day. Last talk is by Noam Finkelstein from, I believe, Cornell University. So he will present remotely. He will talk about parameterization and cardinality bounds for latent variable graphic models. Okay, go ahead.
Great, thank you. Thanks very much. Thanks for having me. I'm sorry I can't be with all of you. I'm very sad to be missing the in-person part of the workshop, but I'm happy to be here virtually. So I'll be talking about work with Ellie Wolf and Ilya Spitzer, who are both there in person. So you can follow up with me or with them after the presentation. So the sort of big picture goal is of this work is to reduce the number of unidentified model parameters to facilitate computational approaches to causal compatibility and also to inference. And in that way, it's actually related to the sort of closing of Richard's talk. So that was a nice segue. And I think the part that's going to be of most interest to physicists is the causal compatibility question, which Ellie also spoke about yesterday with the inflation approach. So the kind of two main things we're going to do to try to reduce the number of unidentified parameters is find lower non-restrictive latent variable cardinalities in DAG models. And the second approach is going to be to use a hybrid parameterization. I'm going to talk about what that means. So the general setting is we have observed variables V, unobserved variables U. We have some kind of latent variable model for the distribution over U and V. And we call the induced model for just the distribution over V, the marginal model. And when you have a latent variable model like this, when you make assumptions about the cardinality of U, it could be that you're restricting the marginal model. So in this really simple model where A and Y share a common cause, unobserved common cause, if they both have high cardinality and you assume that U has low cardinality, you limit their correlation, and therefore the resulting model is smaller. The resulting marginal model is smaller than if you had infinite cardinality. So the question is kind of what can we say about cardinalities of these latent variables? So we're going to start with a really broad view. We're going to talk about arbitrary models for discrete data. So we're going to suppose that the observed variables can take values in a state space omega of size d. So any model at all for the marginal distribution over those variables has to be a subset of the d-1 simplex. We're not specifically talking about graphical models yet. This is any model at all. And the question is, can we use the finite dimension of the marginal model, the fact that this is a finite dimensional simplex, to find a non-restrictive cardinality for U? And the answer is yes. And this is commonly done by information theorists. And the way that they do it is through Chirothedoore's theorem. And this has also been used to bound latent variable cardinalities in a specific class of DAGs in a 2017 paper, which Ellie was also a co-author on. And the theorem says any point in the convex hull of a set in Rn can be written as the convex combination of n+1 points in that set. So how do we apply this to our latent variable cardinality question? Well, we start by constructing a set in the simplex, which we denote script S. And the set is going to be made up of the conditional distributions of the observed data conditional on the latent variable is equal to little u for every little u in the state space of U. And then we observe that the expected value of this set, taken with respect to U, is going to be just the marginal distribution. So any marginal distribution that's permitted by the complete model is going to be the expected value of this set. And it follows that the true distribution, marginal distribution, is in the convex hull of script S in the relevant simplex. So where do we go from there? Now all we have to do is apply Chirothedoore's theorem. We say that due to Chirothedoore's theorem, this distribution, the true distribution, can be represented as a convex combination of d points in script S, which we denote using this notation. And in this case, we're going to take the distribution, the probabilities that U equals little u, to be the weights of the convex combination, and the conditional distributions of V to be the points in script S. So what that means is that any marginal distribution, PV, in the marginal model, it remains in the marginal model. In other words, we can express it if we assume that U only takes values in a state space of size D. So in other words, the assumption that U has final cardinality of D is non-restrictive. So again, this is sort of like the most general application of Chirotheodore's theorem that I could come up with, but it's an idea that's been applied in many specific cases. And so far, we're not talking about graphical models or anything. This is just saying for any latent variable model with discrete observed data, we can bound the cardinality of U. And you were a little bit glossing over the idea of what if there are multiple latent variables. It doesn't really matter. You can kind of marginalize out the remaining latent variables and apply this to one latent variable at a time. So let's just look at a quick example of a causal latent variable DAG. So if we're considering this kind of causally, then we're modeling the factual version of A, and then counterfactual versions of M after intervention on A, counterfactual versions of Y after intervention on M. So if we assume the variables are binary, we get 5 random variables. And so the sample space for the observed variables is 2 to the 5. So it's a combinatorial space. It's 32. So we can say that the one bound for the cardinality of U, or one non-restrictive cardinality of U, is going to be 32. People often talk about these as bounds on U, and of course U is sort of like potentially infinite dimensional, and you can't really bound it. So I like to talk about non-restrictive cardinalities or bounds on non-restrictive cardinalities. Okay, I don't know if I would notice if anybody had any questions. So I hope somebody will tell me if so. But I'll just continue until that point. So if we kind of just extend the idea we just looked at to apply these to apply the same idea to causal latent variable DAGs in general. So for each observed variable in the DAG, we have to model one variable for every setting of its observed parents. These are the one step ahead counterfactuals. And what that means is, if we let script x sub v and script x sub parents of v denote the state space of the variable v and its parents respectively, then the total sample space for the variables that we're modeling is going to be given by this product. And if you have, this can get really big really fast. If you have multiple parents of v, then you have this kind of combinatorially sized thing, which is anyway in an exponent. So this is kind of our starting point, and then our question is, how much can we improve on this? And this is the same cardinality, the same non-restrictive cardinality applied at the district level, not at the graph level, that was given in a recent paper, a 2021 paper by Zhang and company with a very different proof strategy. Okay, so there are a number of really simple things that we can do to reduce the cardinality bound. So we're going to start with kind of the simplest of them, which is to say the number of variables that we need to model kind of depends on what we're interested in. A couple of slides ago, we considered sort of the causal model, so all of the one step ahead counterfactuals. But it could be that if we're interested in something like causal compatibility, we only need to model the factual random variables. So if we only model the factual random variables, there are only 3 of them. We get a sample space of size 8, and we can therefore say, if we assume U to have cardinality of 8, that's a non-restrictive assumption. More generally, we can kind of pick and choose which counterfactuals we want to model. So if we're interested in some kind of inference question, causal inference question, we might want to model counterfactual versions of Y, but we might not care about counterfactual versions of A and M. So you can end up in a scenario where if you have kind of factual A, factual M, and then the 2 counterfactual versions of Y, you have 4 random variables, and therefore you get a cardinality of 16. So the kind of thought here is that the non-restrictive cardinality actually depends on what we need to model in terms of the counterfactual variables. The less we model, the lower the cardinality. And I think in most applications, you don't end up needing to model all of the counterfactual random variables. And so this is maybe slightly unintuitive, which is that if you want to kind of answer a causal inference question, you end up with a different non-restrictive cardinality than if you want to answer a causal compatibility question. And that's just because you're modeling more variables. Okay, so the next kind of simple thing we can do is we can notice that equality constraints reduce model dimension. So now let's assume we're only interested in the factual random variables. We have maybe a causal compatibility question. So we don't care about counterfactuals. So we only have 4 variables here. And if variables are binary, then any model over these 4 variables is going to be a point in the 15 simplex. In addition to this information, we also know there are 4 equality constraints due to the structure of this model. 2 of them are from z being independent of m given a, so you get 1 for each value of a, and then you get 2 from z being independent of y after intervention on m, which is an identified distribution. You get 1 for each value of m. And so using these 4 equality constraints, we can say the real dimension of the model is 11 instead of 15. Why is that? Because 4 sort of dimensions of the model can be exactly are deterministic functions of the remaining dimensions. And so visually, we can kind of think about this as lower model dimensions goes to lower cardinality bounds. And the reason is that if you start off on the right-hand side and you have this sort of blue blob represents the model in the simplex, and you kind of, if you know you have an equality constraint, what that means is that one of the dimensions is not really there. And you can just project onto a lower dimensional space without losing any information. And then you can apply Chirotheodore's bound in a lower dimensional space. And if you remember, the bound is just in terms of the dimensionality of the space. So you get a lower non-restrictive cardinality. Okay. So aside from that, we can keep going. So even once we reduce the dimensionality of the model through these kind of simpler ideas, we can notice that the distribution that some of the dimensions that remain might not be relevant. So the distribution of U isn't going to touch several of the dimensions, and I'll explain what I mean by that in a minute. But the sort of intuition is that no matter what you do to U, you're not going to change the marginal distribution of Z, and you're not going to change the conditional distribution of M given A. So no matter what you do to U means that you can change its distribution, you can change its cardinality, you can do whatever you want. And so in some sense, we should get a discount for these points that U isn't going to be able to change. So how do we encode that? We use nested Markov parameterization. So this is a really nice parameterization for the nested Markov model, which was introduced by Robin Evans and Thomas Richardson, who are organizing this workshop. So it has the parameterization has 2 really nice properties. The number of nested Markov parameters is equal to the dimension of the nested Markov model, which has been shown to be equal to the dimension of the marginal model, I believe also by Robin Evans, which means that you get essentially 1 parameter per dimension. And the second really nice property is that each parameter has a causal interpretation, and the causal interpretation can be used to obtain a graphical criterion for relevant latent variables for each parameter. So let's look at that more closely for a moment. So if we again return to this graph, we'll consider nested Markov parameters for this graph, or at least one of them. Nested Markov parameters in general take the form of being the probability of some event conditional on the probability that a set of variables, observed variables A, takes certain values, conditional on observed variables B takes certain values under intervention on C. So in this case, one of the nested Markov parameters is the probability that upon intervention A equals 0, the variable M takes the value 0. And so we can represent the sort of model for what happens when you intervene on A with the Swig graph, which has been discussed in previous talks. But if you look at this graph, you'll notice that U is independent of M after intervention on A. And so what that means is that no matter how I change the distribution of U, nothing about this probability is going to change. And in particular, if I alter the cardinality of U, nothing about this probability is going to change. And so the kind of Sorry, I'm seeing a question in the chat. Irrelevant for the effect of A on Y. So the idea of relevance, so the question in the chat is irrelevant for the effect of A on Y. I'm going to, is that from, okay, so I'm going to try to address that as best as I can. And then if I have not addressed that well, maybe there could be a follow-up. But so the idea of relevance that we're talking about is not so much for any particular causal parameter. What we're looking for is nested Markov parameters that cannot be affected by the distribution of U. So in other words, that are not a function of the distribution of U. So if I change the distribution of U, which nested Markov parameters are going to be are not going to change? Do we already know are not going to change as a result of the model? So in this case, if I change the distribution of U, we know that this probability can't change. So that's the notion of relevance that we're using. I hope that answers the question. Okay. And so the way that we formalize that, the sort of result that intuition leads to is that the cardinality of any latent variable U can, without restricting the marginal model, be assumed to be the size of the set of nested Markov parameters such that U is not E-separated from AI, conditional on BI upon deletion of CI, where AI, BI, and CI are sort of the variables to the left of, to the right of, and in the do conditional for the corresponding nested Markov parameter. And the idea, again, is just that if the latent variable is conditionally independent of an event after intervention, changes in the distribution of that variable, and therefore the cardinality, are not going to affect the probability, so they're not going to affect the nested Markov parameter. And as a result, the nested Markov parameter, that sort of dimension of the model, doesn't need to be considered as a dimension of the space to which Chirotheodore's theorem is applied. So again, using just the same graph, now we're kind of thinking about a slightly different thing, which is a sort of per latent variable notion of dropping irrelevant dimensions. So for a particular latent variable, even if you can't project from a sort of three-dimensional space to a two-dimensional space, even if you don't have a sort of bijective function between these two, it could be that for a particular latent variable, the extra information that you're losing by doing this projection is irrelevant to that latent variable. And so again, we can apply sort of Chirotheodore's theorem in this lower dimensional space and therefore get a lower non-restrictive cardinality.
Can I ask a question?
Yes, please.
So for the nested Markov parameters, do we know its cardinality? Like how many parameters do we have given a model?
So there's an algorithm, and actually I'm probably like the 20th best person in the room to answer this question, given that the nested Markov folks are all here. But there's an algorithm that will produce the parameters. I do not believe that there's a closed form expression for the number of parameters given a graph.
Okay, thank you.
Yeah. Although feel free to correct me if I'm wrong. Okay, so why bother doing all this? So I'll give a bit of a simple example that shows kind of the benefit of reducing these cardinalities or finding lower non-restrictive cardinalities. So if we do the simple kind of Chirotheodore cardinality that I mentioned at the start of the talk, which was the one in the Zhang et al. 2021 paper, the cardinality is going to be 2 to the k plus 1 for every latent variable in this chain. So this is a simple example, which is just a sort of sequence of observed variables x1 through xk plus 1, and each adjacent pair of variables shares an independent latent parent, independent common latent parent. And we're going to assume that all of the x's are binary. And so here we have that the non-restrictive cardinalities are exponential in the length of the chain. If we apply the improved cardinalities based on the sort of nested Markov parameterization idea, we get a sort of different we get kind of much lower numbers. So just for context, when we get to, for example, k equals 11, according to the kind of naive bound or the simpler bound, we would have to say each u has a non-restrictive cardinality of 2 to the 12, which is 4096. And if we look at kind of the non-restrictive cardinalities for each of the u's using the relevant nested Markov parameters, the largest one is 48. And I think it's just kind of worth looking at the shape of these non-restrictive cardinalities. You'll notice that they all kind of look like a pyramid. You start small. You start relatively small, and then you go up, and you reach kind of the high point, and then you go back down, and they're symmetrical. And the kind of intuition for that is that the part of the model that U1 is involved with kind of falls off a cliff immediately to the left. Let's say immediately towards the start of the chain. Kind of can't extend influence past x1. It can only really extend influence in the other direction. And so the kind of scope of its influence, the number of dimensions that it touches, kind of intuitively should be smaller, and that should kind of increase as you move towards the middle of the chain and then decrease again. So as I mentioned, there isn't a closed form expression for the number of nested Markov parameters, and we also don't have a closed form expression for the number of relevant nested Markov parameters given a graph. So it's a little bit hard to figure out exactly how these non-restrictive cardinalities scale with the length of the chain in this case. But if you kind of look, you'll see an interesting pattern, which is U1, the cardinality of U1 scales linearly. It's just for every increase in k, you increase by the non-restrictive cardinality by 2. And U2 also scales linearly. For every increase in k, you increase the non-restrictive cardinality by 3. And in this case, it's by 4. And in this case, it's by 5, and so on. And so it kind of, depending on how you want to count, you could say that the cardinality, the non-restrictive cardinality scale linearly. I think if instead you look at kind of the max cardinality for each length of the chain, you'll get to quadratic scaling. But in either case, it's kind of a somewhat better situation than the exponential scaling. And this is a little bit of, like I said, a little bit of a contrived example. The benefits of doing this are going to be better in sparse graphs. Kind of the more interconnected the graph is, the less benefit you're going to get. And in the sort of case where the graph is completely interconnected in the sense that there's a single latent variable that's a parent of everything, you'll get just the same bound. Okay, I'm going to check the chat. So there's a question in the chat that says, are the nested Markov parameters for the DAG or for the ADMG? And so the nested Markov parameters are for, I guess it depends on how you want to parse that question. The way I'm going to choose to parse it is that the nested Markov parameters are for the ADMG, but because so the marginal model is going to be a submodel of the nested Markov model, and so because it's a submodel and it has the same dimension, we kind of pretend that they're parameters for the marginal model, which means that there are certain settings of nested Markov parameters that would be outside of the marginal model, which is not the case for the nested Markov model. I don't know if I've answered that question, but yeah, okay.
Repeat, what's the question?
Sorry, the question was, are the nested Markov parameters for the DAG or for the ADMG? And my answer is pretty much, so what I understand this question to mean is that so an ADMG is a graph with two kinds of edges, directed edges and bidirected edges. And the bidirected edges come about by projecting out latent variables and replacing any, introducing bidirected edge between any two observed variables that share a latent parent. And ADMGs, I think, tend to be associated with the nested Markov model, which is a supermodel of the marginal model of a latent variable DAG. And so the question was, are the nested Markov parameters for the DAG or for the ADMG? And my answer is we're using the derivation for the ADMG for the nested Markov model in addition to a result that says that the nested Markov model is the same dimension as the marginal model. But I can go into more detail on that later or as desired.
Ask a further question to clarify you mentioned the dimensionality also related to what kind of counterfactuals you want to model. So this reduction for arbitrary counterfactuals, or it's just for observational distribution?
Yeah, that's a good question. So the nested Markov reduction is for the observed. It's for the not for arbitrary counterfactuals. It's just for the observed data distribution. So if you want to model if you want to model all counterfactuals, then it doesn't really matter. You need kind of the well, I guess it gets very complicated when you start thinking about modeling some counterfactuals or applying something like the nested Markov parameterization to modeling all counterfactuals. And that's something that we have thought a little about, but is not. I don't have any good answers for. So yeah, so the nested Markov reduction is in this case for the observed variables.
Okay, thank you.
Okay. So far we've talked about basically reducing the cardinality or non-restrictive cardinality of latent variables. There is one other kind of way of thinking about this that I'll introduce here. So if we look at this very same graph, one way of thinking about U1 is that it's going to contain all of the information shared between x1 and x2. And so what that means, it's going to contain at most all of the random noise necessary to determine the value of x1. We can assume non-restrictively that it's not going to contain more than that, because if it did, then that noise just doesn't have to be shared between x1 and x2 and doesn't have to be part of U1. So that requires that U1 only has to have a cardinality equal to x1. In other words, x1 can just copy U1. X1 doesn't have any other parents, so it doesn't need to specify any other response functions or anything like that. And you can kind of continue along these lines. You can say, well, if U1 sort of determines x1, then U2 is going to determine x2 in response to U1. And you can kind of continue all the way down the chain. But the problem is that the required cardinalities explode very, very quickly. By the time you get to U4, you're already 2 to the 513. And this idea of tasking, especially in a context like this, is very closely related to gearings and functional models in another paper by Robin Evans. But the sort of one thing to point out is that by the tasking logic, U1 can be assumed to have a cardinality of 2, and that beats the previous non-restrictive cardinalities for U1, regardless of k, for any k. And so we can use these kind of tasking-based cardinalities in conjunction with the improved Chirotheodore cardinalities, because neither one requires us to, neither depends on the cardinalities of other latent variables. Okay, how am I doing on time? Okay, 10 minutes. So I'm going to talk a little bit more about the idea of tasking and the idea of a hybrid parameterization. So I think many of you will have seen representations of causal models that look like this. And the kind of interpretation of these models is that the epsilon variables encode all of the randomness about each of the other variables. So one way to think about this, and this is the way that Balka and Pearl, I think, first introduced thinking about the IB model, and has been discussed earlier today as well, is that these epsilon variables actually encode response functions of each of the variables to its parents. So the epsilon variables actually take a value in the state space of functions from the values of the parents of a variable to the values of that variable. So one way to think about tasking is making the assumption, and you can do this non-restrictively in the same way that Balka and Pearl did it, making the assumption that a common parent of two observed variables contains all of the noise relevant to determining each of those variables in response to their parents. And so in this case, if we say U is tasked with determining A and Y, all we're saying is that U sort of contains epsilon A and epsilon Y and doesn't contain anything else. That means it has to take a value in this sort of cross space of functions of parents of A to A and parents of Y to Y. So if we think about parameterizations, so again, one of our goals was reducing unidentified parameters. Thinking about parameterizations, once we've done this kind of tasking, only U and epsilon M are random. A, M, and Y are determined by U and epsilon M. And what that means is we only have to parameterize the marginal distributions of U and epsilon M. We don't have to parameterize anything else. And that might reduce the number of parameters, which we'll look at more carefully in a moment. It turns out we can do a little bit better than this in terms of the number of unidentified parameters. So if we again think about this kind of conception of tasking U to determine A and Y, we'll notice that epsilon M is not identified because the probabilities of each response function of M to A is not identified. But the sort of conventional conditional distribution M given A is identified. And so what that means is that we can parameterize the distribution of U functionally in terms of this kind of idea of tasking, in terms of a distribution over elements of this space here. But we can parameterize the conditional distribution M given A using conventional DAG parameters, which are identified. And that means that we don't have to add additional unidentified parameters. So the sort of basic idea of the hybrid parameterization is that we have this tasking option. If we task a latent variable, it's often going to increase its non-restrictive cardinality relative to the Chirotheodore bound, but it can reduce the total number of parameters because you don't have to parameterize the distribution of the observed variables. And so the idea of the hybrid parameterizations is that we task latent variables if doing so decreases the number of unidentified parameters. Otherwise, we just use the Chirotheodore bound with the standard DAG parameters. And the approach to figuring out what we task and what we use the Chirotheodore bound at this point is pretty heuristic. We don't have like an optimal way of doing it, but we have some ideas about it. So let's just run through an example of what that looks like. I'm going to pull up the same graph again. We've tasked U to determine A and Y, and then we're going to use the DAG parameters for M. If we were to just use the DAG parameterization, so if we were to find the best non-restrictive cardinality of U that we could, and then parameterize its marginal distribution and then the conditional P A given U and so on, we would get 25 total parameters, and 23 of them would be unidentified. The only two that would be identified are for the conditional distributions of M given A. If we do the functional parameterization, which is we task U with determining A and Y, and then we parameterize the noise term for M, we have 10 parameters, which is fewer, but they're all unidentified because they all involve counterfactual information, cross-world counterfactual information. And if we do the hybrid parameterization, which is what I talked about earlier, which is we task U, but then use the DAG parameters for M, we get 9 total parameters, and only 7 of them are unidentified. So this is the kind of thing we can do with the hybrid parameterization. So the idea of tasking can get complicated. I kind of gave a really simple example, but there are a few complications. So suppose we say we want to task U1 with determining A in response to Z. So in other words, U1 is going to contain all the noise necessary to determine A with response to Z, in response to Z, and U2. That's actually one complication not mentioned on the slide. So if we know the bound for U2, then we can say how big does epsilon A have to be, and assume that epsilon is a subset of U1. The problem is that if that's all U1 is doing, it can't contain any noise that's relevant to Z and Y, but not relevant to A. And that alters the model. So if we say U1, all U1 has to worry about is determining A in response to its parents, then we're going to lose shared information between Z and Y because there's no other avenue for shared information between Z and Y that's not relevant to A. And so to task in a way that's non-restrictive, we have to add a few kind of caveats. So you can only do this kind of tasking if, one, U shares no children with the previously tasked variable, and two, the case that we just discussed, a new unobserved parent of an undetermined children of U is added to the graph if one does not exist. So in other words, if we decide U1 is going to be tasked with determining A, then we have to add a new parent to capture the remaining spillover randomness that's shared between Z and Y. And this is a typo repeat of 1. Sorry about that. Okay, and so now really briefly to wrap up. So, as I said at the start, the goal is to kind of improve computational tractability for causal compatibility and inference questions. So we went through sort of improved non-restrictive cardinality bounds, which are of interest in some cases themselves, but our main goal is to kind of consider this polynomial system formulation of marginal models of DAGs. And so it's sort of, it was recognized, I think, a long time ago, for example, by Geiger and Meek, that a distribution is in the marginal model of a graph if it can be expressed according to this polynomial equation with one equation for every setting of the observed variables. And we get a summation here instead of an integral because we can assume non-restrictively that you take values in finite state spaces. And so we can solve the causal compatibility question by checking whether there are values of unidentified parameters on the right-hand side of these equations that satisfy all of the equations. If so, then the distribution is in the model. If not, then it's not in the model. The problem is that the runtime of these satisfiability algorithms is exponential in the number of unidentified model parameters. And so that's why we're trying to reduce the number of unidentified model parameters in all these ways that I've described. So let's just look at a quick example of that. I guess I'm kind of running low on time, so I won't go through this in detail, but this is just the polynomial system that I described where unidentified model parameters are given in red, identified ones are in blue. As Richard mentioned, I think he was discussing the linear case, but this is also noted in the Zhang et al. Paper that I've mentioned a few times. You can also do polynomial programming to do causal inference, to address causal inference problems. We also have some work on this with colleagues from UPenn. Yeah, and I guess I'm going to just skip through the last little bit and get to conclusions. So the kind of takeaways from this talk are, so even a simple model can have a lot of unidentified parameters, but there are a number of things that you can do if you're using one of these computational methods that scale in complexity with the number of unidentified parameters. So you can improve the non-restrictive cardinality bound, you can use the hybrid parameterization. These two are in the slides that I skipped, but I'd be happy to answer more questions about them. And the last thing that I want to mention is that if you look at these polynomial systems, they have kind of a very, very specific structure. So you have these, all of the equations in the system have the same number of terms, all the terms have the same degree, and so on and so forth. And I think there's probably a polynomial satisfiability algorithm that can take advantage of that structure. There's also kind of a very specific structure in how parameters are shared across equations. And so in terms of speeding up causal compatibility queries, I think that is an interesting venue for future work. So, yep, I think that's it. That's it for me. So thank you very much for listening.
Thanks for the talk. I have two questions. One about, I guess, a clarification question. Can I go back to the slide where you mentioned the complication of tasking, where you have to split the U? Yeah, that one. Yeah. Oh, I guess, yeah, I misunderstood. Yeah, I think that's fine. Okay. So I guess my main question is, do you have any idea about proving a lower bound for this type of problem?
That's a really good question. So I think in some cases it's easy to prove a lower bound, and these are kind of trivial cases. So there's there's a paper also by Robin Evans, whose work has clearly influenced this work, but where he presents a sort of criterion for latent variable DAG equivalence. And one of the results, which I think actually this specific result was known before that as well, is that these two models, the marginal models of these two latent variable DAGs are equal. And so of course that means that the lower, the non-restrictive cardinality of U can be 0. You don't need it at all. So that's a little bit of a trivial answer. In general, in cases where that doesn't apply, I haven't spent a lot of time thinking about lower bounds, and I don't have a good sort of non-trivial answer to that question.
So, this is Thomas. I just wanted to follow up on the question I think that Jin asked about what was the nested Markov model parameterizing. And so it is also parameterizing. It is parameterizing the observed distribution, but it's also parameterizing all of the identified causal intervention distributions.
Great. Thanks for that clarification.
My understanding, nested Markov model excludes inequalities. Does that have any impact on this parameterization cardinality? No.
So, yeah, it shouldn't. And that's because the nested Markov model has been shown to be of the same dimension as the marginal model. So if it I guess it would have been plausible that the marginal model had lower dimensional, which meant it would have included equality constraints not captured by the nested Markov model. And in that case, there would be a way to improve this cardinality by taking advantage of those equality constraints as well, but that's been shown not to be the case. It captures all of the equality constraints.
Any other questions? Okay, let's thank speaker again.
Thanks very much.
So Frederick has an announcement.